Hi, welcome to the NASSCO Safety Podcast. My name is Dennis Pivin. I'm your host, and today I have with me Chris Macey, and we're going to be talking about safety and design. Chris,
Yep.
why don't you tell the audience a little bit about you? Wait a minute, before I have you tell the audience, right? You were just awarded the Trenchless Technologies Person of the Year Award. Congratulations.
Thank you.
Thank you. And how many years have you been in this industry?
I started with my legacy company March 1st, 1978, so about 47 years, I guess.
47 years.
Yeah.
That's amazing.
I show
That's
no
amazing.
signs of growing up.
No, not at all.
Yeah.
Well, thanks for coming in today, right? So we're going to focus on telling about some projects
Yep.
that involve design, but safety engineering gets broken down into a couple of categories, as you've explained this to me, right?
Mm-hmm.
And those two categories are design engineering and implementation engineering.
Yep.
Do I have that right?
That's correct.
Okay, so
Yeah.
I want you to explain to our audience on the podcast, let's start with design engineering.
Yeah.
What does that look like from a safety perspective?
From a safety perspective, appreciate that most designs focus on solving a problem. And one thing that you cannot lose sight of is that if you can't, you can solve the problem. It's like I can design anything, but can someone build it? And the reality is that it's not only can someone build it, but can someone build it safely? And the other aspect of design that the sooner you start thinking about it, the better, is how do you do verification? Well, sometimes verification is very risky from a practical perspective, so there's risks associated with it. So the sooner you start to focus on those things, quite frankly, the easier in the implementation phase it is to realize that safety is, another component of the work, not just another component, but a critical component. Because if I can't verify it, if I can't, do it safely, if I can't implement design, then quite frankly, it's a crappy design. It's,
Okay,
yeah.
right. Yeah,
Yeah.
it's not what you want.
Yeah.
So I know you've got experiences with this, like the shared real life experiences that you
Yep.
have. So could you tell me a project in your view of things over your lifetime, what was a poor design that didn't have safety in it? What would that project have looked like?
It would look like someone exposed to a situation that just you should never find out about it in the construction phase.
Okay.
Someone being asked to go into a place that either wasn't safe or realizing once you got there you're in an unsafe situation, because it's not that the unexpected can happen, but if you don't think about the unexpected,
Right.
it absolutely will happen.
Wow.
And that's a really, really critical to it, because if you haven't thought about it, if you haven't thought about the things that could go wrong, then you haven't thought about enough to go to construction. And that's a really, really critical aspect of design and just practical common sense in the context of understanding risk.
Absolutely.
Yeah.
And what it allows us to do on the safety side, by your engineering in the safety,
Yep.
on the design phase, we can do the pre-planning phase.
That's correct.
Before the project ever starts. Because we partner with design engineers, right?
Yep.
Once you identify what that safety risk is,
Yep.
and your proposal on the design,
Yep.
then the safety professionals come in and they say, well, we can help implement this, and we can train on that, and we can do these, right?
Yep.
So we got that outlined.
That's correct.
Okay, let's transition to engineering, design, implementation. And what's the difference?
Yeah, the critical thing about the implementation of it is it's real life, so that by definition, the bar is raised. There truly is risk. Like things can start to happen because you're playing with real machines, real programs.
Okay.
I think one of my first exposures to it, aside from normal job risks that you might see, was I spent about 10 years in the 1990s to early 2000s working on the Shoal Lake Aqueduct.
Okay.
And
where is that for our audience? Not everybody may know where that is.
Understood. It's in Winnipeg, Manitoba.
Okay.
It's a famous pipe because it was designed by the same people who designed the Catskill Aqueduct into New York.
Okay.
It was built from 1913 to 1919, and had never really been inspected until the 1990s.
Really?
Yeah.
How many years? So I'm trying to do the math. That's a long time to not inspect a pipe.
It's a long time that you're going into a pipe that you know very little about.
Right.
Yeah. So by definition, and then it's 97 miles long. About 83 miles of it have literally conveniently an access point once every mile. So
Wow.
by definition, and this predates kind of putting robots in there. We're going to take another run at inspecting that pipe. We'll put a lot more robots. I can put a lot more automation. I can put a lot more tools. But in the 1990s,
It was visual.
used our eyes.
You had to put people down
We had
there
to put people down there.
to do this work, right?
Yeah. And we had to do it for not once or one off, is that we had to do it for about a 10-year run.
Wow.
So again, it's not about figuring this out once, but it's about not only thinking about safety, thinking about confined entry, thinking about access, the legitimacy, but honestly practicing it. Make sure that we never, you can't get soft about this stuff.
Right.
So
right.
we, in an annual shutdown, we would always practice rescue as a minimum. Like we'd think about all the different silly ways that a human being could slip and fall, or how that we staged work that promoted isolation of people, because we would be doing. It wouldn't be unusual to be doing a shutdown that had some construction, some assessment, and we might have, and it's not an exaggeration, literally about 200 people that we had to understand where they were and where they were working.
That you took away my next question. I was wondering how many people are on a project this large, and it's 200 people.
You're taking the whole water supply to a city of about 600 to 700,000 people out of service.
Wow.
So timing, doing as much as you could, the emphasis on production is very, very high,
right?
Yeah.
And how did they do a bypass while you were doing this? How
We
did they keep
had
water?
reservoirs at the termination of the aqueduct, so they basically had, in theory, they had a month's storage if everything went well. To give you some sense of things going wrong, one of my early years in the aqueduct program, we literally, not an exaggeration, we literally had a plane. There's a little farmer's field just beside us. We literally had a plane with about, I don't know, maybe 5 gallons of gasoline in it, but literally a plane fell in, and tragically the fellow died in the plane. He died in one of the reservoirs, but it took 1/4 of the water supply away on day one.
No, oh my gosh.
So safety, yes, no, we
That's
didn't
just
anticipate
amazing.
the plane,
Right.
but we had to respond to it in the context of it. He was rescued and couldn't do anything about it. It wasn't anything to do with their job, but
Right.
that's the reality of it. There's termination storage, and yes, a little bit of gasoline in it wouldn't kill everybody, but literally at that time, just you measured that in parts per billion, it's a big risk.
It
so
is.
Literally it takes the whole reservoir to service.
Wow.
So that's how the balance is. So the focus on you is that you've got to get as much done over as large an area as possible every time someone turned that water off.
That's amazing. So I'm going to come back to the design again on the project.
Yep.
You mentioned that the manholes were a mile apart.
Yeah.
And we don't see that typically anymore.
No.
So would you be able to opine on why you think they did that? Did they put the manholes every mile?
They did it because it was built in 1913 to 1917,
no
and
way
that
to
was
get in
pretty
there.
logical. That's actually, to them, seemed like a lot of manholes. You know what I mean? Like from a practical perspective, do we really need these?
Right.
The phenomena of drag was not well understood.
Okay. For our audience, please
Drag is the
explain
flow
that.
of water. It takes a long time for the water to empty the aqueduct. So your sense is to jump into that water while there's still a little bit of water in the pipe. The design of the arch section actually is to maximize its velocity.
Okay.
So in essence, if you jumped into 10 inches of water, which doesn't look like very much water, it would take a 200-pound person and whip them right off their feet.
Wow.
Just by doing a drag calculation. So again, trying to anticipate conditions that might appear safety, but make sure that you're cognizant of what it means in the context of response. So,
Oh, I think that's great from a safety perspective.
Yeah.
You hit the nail on the head there, right?
Yeah.
How many engineers in their design have to worry about water drag,
Yeah.
the way you described it, I would just wonder, do they really do it? Do they really think
They
that
did.
deeply?
And the only reason that I was cognizant of calculations of that is I got hired, again, as a young engineer to investigate a boy dying, about a 14-year-old boy tragically dying in about 10 to 12 inches of water by having to understand why flowing water in a ditch is a risk.
It's dangerous.
Yeah.
Yeah, coming back out of the pipe for a minute when we talk about flooding,
Yeah.
and we hear don't drive through flooded roads.
Yep.
That's the reason.
Yeah.
Because of the drag, right?
Yep, exactly.
And it moves vehicles.
Yep.
At very small inches amount of water.
Yeah, and something as simple as a 4-inch diameter object with water flowing on it of velocity, you can produce a little. You don't need anything more than Excel, but you can estimate the force. And once you get the force in perspective, you realize 10 inches of water moving at a decent speed is a risk, is a huge risk, because the only way to put human beings in there, if you are going to do something that silly, is essence literally to tie them off. You know, like you can't just jump in water.
Can't
like
just
that.
go down there,
Yeah.
right? You know, there was a project that you and I worked on in British Columbia,
Yeah.
Highbury Siphon.
Yeah.
And I thought we had some great experiences about safety to share from that project.
Yeah.
So I'm just going to kind of flip it to you. And I think we'll start with, you had to do some inspections in the pipe. And I was on site to do the rescue. We had a rescue company and my team there when you were getting ready to go in and take this sample. So explain the Fraser River to our audience who may not know where that
Fraser
is.
River is a huge river that carries a lot of water and drains through a big chunk of the province of British Columbia in Canada out to the Pacific Ocean. And where we had 3 pipes that were being lined.
And they were called interceptors, if I remember right.
Interceptors. They literally are the last pipes that go into the sewage treatment plant. I own a sewage treatment plant. And the Fraser River at that point was 75 feet deep. So 75 feet of hydrostatic stress and a pipe that leaked. And the reason that we were going in particularly was because, in essence, after the liner, it still leaked. It had some deficiencies in it that we had to both investigate and understand what those deficiencies were and whether they could be fixed, you know, but we physically, the only way to get at them was to look at them. And plus to do remedial work of it, you know, never mind, you know, of capital costs, but it was just logistically it wasn't as simple as say, well, just throw another liner in. And we had rationalized that, you know, kind of what was there. We had sampling and could anticipate what the problem was, but you needed to prove it out. And part of proving it out was using injection grouting to stop it from leaking, because that was a very reliable way to stop it from leaking. And we knew that technology, and we could see that. You could examine each aspect of it. But the challenging thing was we needed to know the mechanical properties of the liner at the bottom of the siphon, because we could visually see it was a little bit different than the top of the siphon.
And that's why you had to go in there.
That's exactly correct.
Somebody had to cut that.
Yeah.
I remember that.
Yeah.
And we were hauling the tools in.
Yeah.
And, you know, I remember when this project, before the lining started and you had to do this work,
Yeah.
that was leaking
Yep.
already
That's
before
correct.
we lined it the first time.
That's correct.
And I remember our crews having to go down there, and our rescue team, you know, we had radio communication, we had retrieval systems. But again, to your point, 75 feet of water above their head. I forgot, what was the diameter of that pipe?
The liners were 68 inch, so
68
probably a 72 inch diameter and all those
Yeah,
sides.
so we're talking pretty good sized pipe,
Yeah.
right? That you can walk through. But for our audience to kind of think, you're down into this very large pipe and you have a very big river over your head, and it's leaking on your head while you're trying to patch holes prior to putting a liner in.
Yeah.
So from the safety perspective, we had a recovery team on site. They had scuba diving gear in case something terribly went wrong, and we had to, you know, get in the water to get them out. We had retrieval lines on, we had ventilation, we had permits. We were following every critical component of confined space entry from the very beginning that we had to. And I remember in Vancouver we had Be Safe.
Yeah.
For Vancouver, it had actually come out and went over the pre-plan with us
Yeah.
prior to this, just because the risk was so high.
Yep.
So then we did the initial patching before we lined.
Yep.
And then we had our rescue team there during the lining. And then there were some challenges with the liner, as you explained.
Yep.
And now your team had to come back in
That's
and go
correct.
in and cut a hole. So we had the same rescue teams all lined up for you as well.
Yeah, and appreciate, again, you don't make rash decisions, that the decision to go in was accompanied by literally delaying going in, because the risk of the liner falling down in the short term was very low. We could see that structurally.
Okay.
But the risk of the liner lasting forever was also very low, based on, you know, it can't perform like that forever. So the two things that we did over the course of the winter to prepare for going into it, to you know, assess its residual strength, is I reviewed the mechanical properties of the siphon. And this is interesting, this is a true story. I reviewed them from the safety of the structure.
Right.
And I look at the stress versus strain curves. I look at the ductility of it, the ability of the siphon to last. The stress versus strain curves of that are like, it was a textbook. They're like more than 5% strain, and so you could see that the liner itself, we had good knowledge that the liner itself was were saving, that it was a good liner, but it leaked. And we had to do back calculations structurally, so I had to model it to understand how big a piece I had to cut out. I wanted to make sure that the pieces that we cut out, in essence, could be tested, so I sent them to a lab. Marshall Gibbons, my good friend, who was game to go down and is very, very safety conscious himself. He does not take risk.
Right.
Marshall practiced all winter in terms of, can I really do this? Because we had to cut out about a little over half the wall.
Wow. I do remember that. I remember him telling me he practiced.
And then the same people who helped us, we would not go in without residual plan, because we realized that a reality is we could spring another leak by cutting out. And so we had people with confined entry experience, appropriately equipped to do injection on the fly.
And that was the design. Because I remember even when we went in the beginning of this project, because I had worked with you on this, and I was worried about a collapse, and you ran the numbers, and you said, even though it's leaking, it's structurally solid.
Yes, exactly correct.
And that gave me the confidence, is what I want to point out, on a safety design, because that's what we're talking about here, safety engineering and safety design, right? That, the fact that you did the design and assured me from a safety perspective, we weren't walking into a death trap.
Exactly correct.
But we still needed to be prepared from a safety perspective of something could go wrong.
That's correct.
And that's why I loved working with you on that project, because I learned so much about safety engineering and safety design, and then when we had to do the implementation. So this is a fantastic story. I appreciate sharing.
To close it, just to show that stuff happens, okay? And just like the aqueduct story I shared with you, is a true story, you don't count on a plane flying. When we had the siphon dewatered, we basically had a tremor. We had an earthquake. We had not a major earthquake, but again, those same characteristics of what do you need to be seismically resilient are, in essence, the strain calculations. All the things we did to look at integrity basically made it safe to literally take a little shake from the earth to let us know, don't get overconfident, okay, in terms of the stuff. So,
right. Look at all perspectives, even when you think they're pretty
very, very low.
Low
It's human life, and it's very, very critical.
Absolutely. So this has been great. I think these stories really help our audience understand what we're talking about with safety engineering. But as we try to wrap this up, for new engineers that are coming into this industry, what would you tell them about safety engineering and design and implementation? What would be some critical words of wisdom you could share with them?
I think, first of all, is that it's something that you look at in feasibility stages. The earlier you start looking at, the better. And engineers are notorious for thinking they have to solve every problem themselves. The reality is that, and that I've learned with you, is that you know a lot more about how to make things safe. I can have stuff that I know scares the bejesus out of me, but I know when I go and seek someone from a professional perspective that understands safety, we can work on it together and collaborate and put it in perspective and mitigate it. So the sooner you engage someone in that, the better. But if you're not thinking about it, it's very, very difficult from someone from your background to come in and say, so what, to understand what's doing and what can go wrong. So,
I can't do it without you.
Yeah, so it's fundamental from the initial stage. And then I think the other one that is a huge lesson is designers tend to think that their job's ended when they've pumped out a piece of paper.
Really?
And as a designer, your job is not finished. I can assure you, if you think it is, you'll have a surprise someday when you're sitting in examination for discovery and a lawyer, okay? So think about constructability, implementation. Okay. And again, you don't have to do it, but you do have a duty to sit there and articulate risk, articulate that and make sure that reasonable controls are taken to the people who own the infrastructure.
Awesome.
And those are critical lessons to understand, that it doesn't stop with what you think you're doing for the problem, is how does it get built, how does it get verified, how can all of that be done safely.
Well, Chris, this has been awesome conversation. Thank you for sharing your stories and getting out the word on safety engineering, what that's about. Thank you so much. I hope you enjoyed our topic for today. Thanks for joining the NASSCO Safety Podcast. For more information on safety topics, please go to nassco.org, click on safety, and choose your safety topic.